Hey guys, this is Miss Garner, and we will be going over the rotations and dilations Jamboard. So remember last week we covered our first two movements, which was a translation, which means slide, and a reflection, which means flip. So our third movement is a rotation. You should have heard the word rotate before in your life, and know that just means to turn. So if we look at our two pictures, this picture of the F, notice it's turning around this fixed point, the origin. This way it is turning clockwise. And notice that also our triangle, it is turning about this arrow, or sorry, this cross right here, and it is turning counterclockwise. So notice that the shape does not change, the size does not change. The only thing it does change is which way it's facing. We call that the orientation. So here are some examples of where you see rotation in the real world. This is probably the easiest one to come up with examples because you see it all over the place. So for instance, the Earth, it rotates on its axis, which creates our day, right? Every 24 hours, it rotates on its axis. It's also rotating around the sun. So that's what creates a year for us. Also, windmills. If you have ever driven on the road from Louisville to Chicago, you should have seen some windmills along the way. This takes these big needle point things, and when they rotate, it creates energy. And then finally, a merry-go-round. You're sitting on a horse or a tiger or a lion, and you're rotating or turning about that middle point. So all of those are examples of rotation, or instances where you see things turning. So in this red box, what you need to do is come up with one more example of what rotation you see in everyday life. You can use a sticky note, you can use the text box, or you can use the drawing tool to write out your answer here. On slide 3, this one, you will see that we have our two triangles. One of them has already been rotated, and we just want to describe it. So we know it has turned. We want to say in more description how it has turned. So just a little review. Remember that our pre-image is our first shape. Our image is our second. We also know this because if we look at our pre-image, you will see that it's just regular letters, X, Y, Z. Our image, though, it's hard to see, but they have those little dash marks after them. X prime, Y prime, Z prime. So we know it is turning from blue to red. So the first thing we want to ask is this a 90 degree or 180 degree turn? So remember a 90-degree turn in our Pythagorean theorem unit, we said it looked like this, right? It's a sharp corner. There's a box there. That's what 90 degrees looks like. On the other hand, 180 is going to be a straight line. So if you think about if you're standing up, a 90-degree turn, you'll be facing sideways. A 180-degree turn, you will be facing backwards. You go all the way around. All right, so in our graph here, the easiest way to be able to tell is that a 90-degree turn, it will be in the quadrant right next to it. So you will see our grid, we have 4 quadrants here, and our triangle, you'll see 1 to 2, it's in a quadrant that's right next to it. So we know that this example is a 90-degree turn. I'm going to use my yellow pen here to show you what a 180 would look like. So if we went totally opposite, so the top left corner to the bottom right, this is the quadrant it would have to be in for it to be a 180-degree turn. All right. The next thing we need to describe is whether this is clockwise or counterclockwise. So if you think of a clock, old-fashioned one, not a digital clock, we'll have 12 at the top, 1, 2, 3, and so on, right? 6, 7, 8, 9. And you have your two hands in the middle. All right, this is kind of what a clock would look like. Well, the direction a clock goes is in the order of the numbers, right? It's going to go in this direction. If your object is turning in that direction, this is what we call clockwise. If it goes opposite, so if it goes the opposite direction of the numbers, so 12, 11, 10, 9, and backwards, that is what we call counterclockwise. So I always, with these problems, draw out a clock so I can tell which direction it is spinning. So if I look at my picture up here, 1 to 2, you notice at the top it's going towards the right as it's going down. So that is going in a clockwise direction. It's going the same way that a clock handle would move. So once again, when we're describing rotations, you need to say whether it's 90 or 180 degrees and whether it's clockwise or counterclockwise. I'm going to let number 2 and number 3 you guys solve on your own. On slide 6, you will see that we have our fourth movement, which is called a dilation. For dilation, this is really just a change in size. So just like the other movements, we have those simple words to remember it. Dilate, you will think change size. It can be either getting bigger, which is what we call an enlargement, or it can mean getting smaller, which is what we call a reduction. So notice that the shape is the same, the direction it's facing is the same, but the size is what is changing. What's really important to know about dilation is the scale factor. This is what's going to tell you whether it's getting smaller or bigger and by how much, right? Is it getting a little bit smaller, a lot smaller? That's what the scale factor is going to tell you. So if the scale factor is greater than 1, that means the shape is getting bigger. So for instance, if our scale factor is 3, it is getting 3 times bigger. If our scale factor is 10, the new shape will be 10 times bigger. On the other hand, if the scale factor is less than 1, so that means it's a fraction, that means the new shape is getting smaller. So if our scale factor is 1/2, our new shape is going to be 1/2 the size of the original. If our scale factor is 1/5, our new shape is going to be 1/5 the size of the original. So with our first we're going to go over some examples. So just like last time, where do we see this in the real world? So first of all, photography. So if you get your school photo taken, you will get the normal 4x6, 5x7 photo, but you will also get, if you choose to order a packet, a large photo that you can put in a frame. You will also get those little wallet-size photos. It's the same thing, right? The picture hasn't changed. It's just the size has. Same thing with food and drinks. If you go to McDonald's, you can get a small Coca-Cola, you can get a medium Coca-Cola, you can get a large, an extra large. The cup is the same, the lid is the same, the Coke is the same. The only thing that's different is the size. And then where you probably see the word dilate the most is having to do with your eyes. So in your eyes, your pupils will actually get smaller or bigger depending on how light it is. If you go to the eye doctor to get glasses, a lot of times they will dilate your eyes so that they can see better into them. More light goes into your eyes. So dilate is used a lot with your eyes because the pupil gets smaller or bigger depending on that light. So what I want you to do is think of another example of a dilation. So think of something where it's the exact same thing, it just comes in different sizes. So it can be something smaller or it can be something where it's gotten bigger. And then finally, our example for describing dilations is we want to figure out what is the scale factor. So that is going to be how we describe how it has changed size. So once again, if I look at my two shapes here, my blue shape I know is my starting point. That's my start because it has the normal letters, P, R, Q. The green shape is my second shape because notice it has those primes afterwards, those little dash marks. So I know that my shape has gotten bigger. It's gone from blue to green, so it's gotten bigger. So I know my scale factor is going to have to be greater than 1. What I'm going to do is I'm going to pick one of the sides of my shape. It has to be either horizontal or vertical because we want to count our units. We don't want diagonal through boxes. So I'm going to go ahead and just pick the bottom one from R to Q. I notice that R to Q is 2 units long. I'm going to pick the exact same side on my new shape. So R prime to Q prime. This is 1, 2, 3, 4, 5, 6 units long. So my first shape, that side is 2 units long, and after it's been dilated, it's now 6 units long. So what I want to think about is how many times bigger did it get? 2 times what is going to give me that 6? The answer here is 3. 2 times 3 is going to be 6. So I know that green shape is 3 times bigger than the blue shape. So my scale factor is going to equal 3. Okay, so the green triangle is 3 times bigger. I know that because I saw that that side from R to Q was 6 and it started out as a 2. So it increased 3 times bigger. We're going to do one more example like this. So on slide 9, which is number 5, once again, we have two shapes. This time they're on top of each other. So our turquoise parallelogram there is going to be our first shape because it has the regular letters A, B, C, and D. And then the yellow one inside of it is our second because they have the prime or those dashes after the letters. So I already see that it's gotten smaller. If it's gone from that turquoise one to the yellow one, I see that it's gotten smaller. So I already know that my scale factor has to be a fraction. I'm going to do the same thing as last time. So I'm going to start on one of the sides and count the units. Notice that I can't use the left or the right-hand sides because they're diagonal. So I'm going to go ahead and use the top. So from A to B, it is 1, 2, 3, 4, 5, 6 units long. And then in my new shape, A prime to B prime, it's 1, 2, 3 units long. So it started out at 6 and it's now become 3. What I like to think about is because it's becoming smaller, I'm going to divide instead of multiply. And I'm going to think to myself, 6 divided by what is equal to 3? And the answer here is 2. But remember, because I'm dividing, the way I'm going to write the scale factor is as a fraction, because a fraction is really just a division problem. So the scale factor here is going to be 1/2. Okay, so another way to think about this, guys, is remember that 6 times 1/2 is the same thing as saying 6 divided by 2. Okay, so that's how I got the scale factor to be 1/2. Because I was dividing. Number 6 is another example that I want you guys to try on your own. For slide 11, we're going to be actually dilating the shape ourselves. So we see that we have this triangle, JKL, and we want to dilate with a scale factor of 1/3. Because it's a fraction, I know my new shape is going to be smaller. Okay, so I can just double check in my mind. I know that it's going to have to be smaller. So the first thing I'm going to do, step 1, is I'm going to write out the coordinate points. Okay, so each of those 3 points, I'm just going to write them out, their coordinate points beside them. So K is at 6, 3. J is at 6, 0. And then finally, L is at -6, -3. Okay, so just a reminder, when writing coordinate points, it always goes X, which is your distance sideways from your origin, followed by the Y, which is your distance up and down from your origin. Okay, so that's your first step, is I'm writing out the coordinate points for my 3 points there. My second step is I'm going to divide each number by 3. And the reason I'm doing this is because my scale factor is 1/3. It's a fraction, so I know I have to divide. It's getting smaller. And I see that the denominator there is a 3. So if I divide each number by 3, I will get my new points. So I'll start up here with K. 6 divided by 3 gives me 2. 3 divided by 3 gives me a 1. Okay, I'm going to continue dividing each number by 3. 6 divided by 3 is 2. 0 divided by 3 is still 0. And then finally, our last one, dividing it by 3, I should get a -2, -1. So I'm going to circle in red this second step because that's how we're getting our new coordinate points. We divided each number by 3. And then your final step is to plot your new points. Okay, so we're going to take those 3 points that we just created and we're going to plot those. So 2, 1, so over 2, up 1, 2, 0, so over 2, and then finally -2, -1. So left 2, down 1. Once I have my 3 points, I'm going to go ahead and connect them. And you should notice that this blue triangle, it's the same shape. It's facing the same way, right? The pointy side is still facing down towards the left. The only difference is it's now 1/3 the size of the pink one. Okay, so that's going to be our new shape after it's gotten 1/3 the size. You have one more example to do, and you will notice that this time we have a scale factor of 4. You're going to do the exact same thing that we did last problem, but rather than divide by 3, you're going to multiply each number by 4 because you know it should be bigger. Okay? And then the very last thing we have to cover is we have 2 new vocab words. The first one is similar. Similar is if one shape can become the other with a dilation. So if you have a shape and you dilated it, the two shapes are considered similar. So they're the same shape, but they're just going to be a different size. All of the other movements result in congruent shapes. So if one shape can become the other through rotation, so that means to turn, reflection, that means to flip, and translation, which means to slide, then they're considered congruent. So notice it's the same shape, it's the same size. They're just probably facing a different direction or in a new location on your coordinate grid.